Hey guys, hi, this is Radhakrishna. Welcome to my channel. Today's video is going to be on coordinate systems and a transformation from one coordinate system to another coordinate system. So let me show you quickly on what we're going to see. So we're going to talk about basically Cartesian, cylindrical and spherical coordinate systems, and then how to go from one to another and how to express each of the coordinate systems units vectors in respect to one another. And also we're going to see a small example of calculating one of these functions in one coordinate system and correspondingly converting it into another coordinate systems, so on and so forth. So today whatever you're going to learn in this video, you can actually apply it in a lot of different applications. For example, if you want to calculate Maxwell's laws for electric field in one coordinate system, and if you want to visualize it in another coordinate system, or many examples as such, so you can do that. And also whatever we're going to do now is basic fundamentals, or it's like the bricks of understanding the coordinate system, so you can extend it to higher dimensions or different coordinate system as such. So let's start by comparing Cartesian coordinate system and cylindrical coordinate system. Okay, so let's do this first. So we know that the Cartesian coordinate system is a right-handed combination coordinate system wherein there are three axes: x-axis, y-axis and z-axis, and you do a x cross y to get the positive z-axis. So this is called as iit-jee. Now there is a point in the 3D space which is x0, y0, z0. Okay, now we want to represent this in the cylindrical coordinate system. So let us define what is a cylindrical coordinate system first. So in the cylindrical coordinate system, the z-axis is not changing from the Cartesian coordinate system, but what happens is that the x and y axis are transformed into new axis called as rho and phi. The rho basically is the position vector or the direction of the position vector of the point x0 comma y0. Okay, basically what happens is that we project this point on an xy plane and we get the point x0 comma y0. So the vector which choice origin and x0 comma y0 is going to become rho, and the perpendicular vector to rho becomes phi. Okay, so this is going to be rho, and the perpendicular vector which completes the iit-jee is going to become phi, right? So this is the cylindrical coordinate system, and the parameter rho here gives x0 square plus y0 square, which is the magnitude of the projected vector on the xy plane, and phi over here is representing an angle tan inverse y by x. So why does these parameters come? Basically is that, you know, if we consider xy plane, okay, for example this is the x and this is the y. Now in the xy plane, the distance from the origin is going to be root of x square plus y square, as it is a position vector, and the phi angle made with the x is nothing but y0 by x0, right? So that is why you got phi is equal to tan inverse y by x. Okay, so now that we understood this, let us actually calculate what are the unit vectors of rho cap and phi cap, because we know that the parameters are these things, okay, the rho and phi. But what is the vector direction? Okay, so vector direction, actually you can see it here itself, is x0 i cap, y0 j cap. So rho basically is in the direction of x0 i cap plus y0 j cap, but this is not a unit vector. Anyway, anytime when we are representing an orthonormal basis coordinate systems, we do it generally in the basis of a unit vector. So if it is a unit vector rho cap, we have to normalize it using x0 square plus y0 square, and then we take x0 square plus y0 square, and this is the rho cap in the cylindrical coordinate system. Okay, also you can observe one more fact, that you know, this is x0, this is y0 in the system, and then x0 by root of x0 square plus y0 square is just going to be cos phi, and y0 by root of x0 square plus y0 square is going to be sin phi. So this is going to be cos phi I cap plus sin phi j cap. This is nothing but rho cap. So this is how you define a unit vector in the cylindrical coordinate system. Now coming to phi cap, so the perpendicular vector to the rho cap, the thing is we have to calculate this from the knowledge that it is perpendicular. So let us assume that the vector basically is in the direction of L comma M in the xy plane, okay, and we know that this vector is perpendicular to x naught comma y naught, so the dot product is going to be 0. So this dot x naught y naught is going to be 0, which implies Lx naught plus y naught m is going to be 0, and L by m is nothing but minus y naught by x naught. So we are having L equal to minus ky naught comma m equal to minus kx naught, okay. And now we know that phi is generally in the direction of minus ky naught comma minus kx naught, and the k is a scaling factor. So if we want to calculate phi cap, it's just going to be the normalized version of this minus ky naught minus kx naught. It's just going to be minus y naught by root of x naught square plus y naught square I cap plus x naught by root of x naught square plus y naught square j cap, which can also be written similar to this way as minus a sine phi I cap plus cos phi j cap. So this is how we represent two of the cylindrical coordinate system. So this is how we design them. So now that we have gone into the both of the axes that are different in the cylindrical coordinate system, we have actually done x-axis, y-axis, z-axis given conversion to rho phi comma z-axis. Because the z-axis is same in both of the coordinate systems, we need not convert them. Okay, now that we have actually understood what these things are, we can also understand the expression of a point in this particular coordinate systems, right? So the thing is, we can say that x naught y naught is already here and there is z here, so we can say that root of x naught square plus y naught square rho cap, okay, plus z naught k cap is going to be a general description of any vector x naught I cap plus y naught j cap plus z naught k cap in the cylindrical coordinate system. Alright, so now that we have understood what is the cylindrical coordinate system, we will now understand what is the spherical coordinate system. Okay guys, so in the spherical coordinate system we have three different axes, and as in you have observed over here that we took a reference to a positional vector and the z-axis was not changing. In the spherical coordinate system we have a z-axis changing as well, and the reference over here is going to be a 3D vector, 3D position vector, as in we just took a 2D vector after the projection on xy plane in cylindrical coordinate system. We are going to take one of the vector as a 3D vector r cap, r bar. Okay, so let me draw x, y, z for you. So this is z, this is x, and this is y. So there is this x naught, y naught, z naught point, and one of the vectors in the spherical coordinate system, one of the vectors is going to be r cap. So one of the vectors is fixed. It's going to be the position vector in the 3D space. Okay, and the other vector is going to be the phi cap that we actually took in the cylindrical coordinate system. Okay, so that is nothing but minus y I cap plus x j cap, by which is normalized. So there is one phi vector, and then you know what is the other vector? It's basically a cross product filling vector, and this is defined by the angle that it makes with the z-axis. Okay, so this is how we define a spherical coordinate system. So the angle with z-axis that this new phi axis new theta axis makes is the theta, and then phi as in similar to the cylindrical coordinate systems, the projection and the perpendicular vector, which is phi bar, and r cap is r cap. So expressing them in Cartesian coordinate system, we have xi plus yj plus zk, which is normalized for a unit vector to x square plus y square plus z square, and the phi cap is nothing but minus y I cap plus x j cap binormalized to x square plus y square. And the other last vector, the theta cap, is going to be in this way, which is going to fill phi cross r. Okay, so this is how it works in spherical coordinate systems. So the triad over here is phi r theta. So phi cross r is theta, r cross theta is phi, and then theta cross phi is going to be r. So you can always say it as r theta phi, because r generally comes in first. Okay, so anyways, we now know r and phi. We're going to calculate theta. Okay, and how we're going to calculate theta is nothing but we're going to use a cross product formula. So we write ijk, and then we put a determinant of it, and then we fill the first vector here. The first vector is phi cap. So let us tell this particular root of x square plus y square as mxy, and root of x square plus y square z square as mxyz. Okay, let us term this as such because it is going to be very long to write. Okay, so in I cap, what does phi cap have? It is minus y by mxy. Okay, and in the j cap direction we have x by mxy, and in the k cap direction there is nothing, so it's going to be 0. And then we're going to fill r cap in I cap, and that is x by mxyz. X by mxyz is y by mxyz. It's going to be z by mxyz. So calculating the determinant of this matrix in a standard formula, we've got I cap into minus y z minus yz by mxy into mxyz, and then you've got 0. Okay, this is done. And then you've got minus j into, you've got okay, so this is, so I cap now, so this is going to be x into xz plus xz plus xz, and then we have minus j into minus yz plus 0. So this is also going to have the same denominator of minus x by xy, mxyz. Okay, and then you've got k cap into, you've got minus y square minus x square. So this is going to be minus of x square plus y square divided by mxy into mxyz. So filling all of these in a clear way, we're going to have x I cap plus y j cap into z minus x square plus y square k cap divided by root of x square plus y square into root of x square plus y square plus z square. So this is the axis, theta axis or theta cap we can say. So here we have all the three unit vectors, x, y, z by root of x square, y square, z square, and we got phi cap, and also we have got the theta cap. So this is a simple representation of things, and then we can also represent x is equal to, so understand that there is a simple z axis. First component of the position vector is going to be put across z axis, right? So z is going to be r cos theta, z is going to be r cos theta. Let us fill that first, r cos theta, and then the remaining part, which is r sin theta, is split among x and y with the phi axis, right? The phi parameter. So the remaining parameter r sin theta will be cos phi with x, r sin theta will be sin phi with y. So these are the parameters x, y, z. which can be calculated given any r, theta, phi parameters, and the vectors are also given over here, the unit vectors. So this is how we actually convert from one coordinate system to another coordinate system using the properties that both vectors are perpendicular, or the third vector is generated by the cross product of first two vectors. So this is how we define a coordinate system and convert into a coordinate system. Now what I want to show you is a small example. Maybe I'll take an example of the gradient. Okay, so this gradient we're going to calculate. So guys, gradient is nothing but a function. Okay, the gradient is nothing but, as you can actually see here, it's going to be dou f by dou x into x cap, dou f by dou y cap, dou f by dou z cap. So basically it's nothing but the change of the function along x cap, y cap and z cap. So this is how a gradient is defined. Okay, now it is also, there are lots of methods actually to calculate if this is the Cartesian gradient. Let me say this is Cartesian gradient, and then we should get a cylindrical gradient also. So some gradient which is expressed in terms of rho, phi and k cap. Okay, so now you can see that the k cap direction doesn't change because the z axis doesn't change. So let us fill that first. Now understand that the only directions which are going to be changed are x and y, because the xy plane is rotated into rho cap and phi cap, right? So how do we calculate this? This is the method which you can do for other functions as well. So let me explain you. So we are expecting something which in the forms of dou f by dou rho, okay, and dou f by dou phi. So we are expecting some things in this form, right? We're going to change this into this. So how do you actually change dou f by dou x into dou f by dou rho and dou f by dou phi? Is nothing but you do dou f by dou of rho into dou f dou rho by dou x. Okay, so the first thing is you change basically, you know, x is nothing but rho cos phi, isn't it? In a cylindrical coordinate system you have rho, you have x here, which is x naught. So x naught is nothing but rho cos phi. So we know that x is dependent on rho and phi, so we generally apply a partial derivative UV rule, and we get dou f by dou rho into dou phi by dou x, right? Similarly we do it for y as well. And when we observe this here, so let us keep this as such. So we have dou f by dou rho into dou rho by dou x. Alright, so we also know that rho is nothing but root of x square plus y square, isn't it? So dou rho by dou x, what is the differentiation of this function? Partial differentiation with respect to x. It is nothing but 1 by 2 root x square plus y square into 2x, isn't it? So it's going to be x by root of x square plus y square. We got this, plus dou f by dou phi, dou phi by dou x, dou phi is, what is phi? Is nothing but tan inverse y by x, isn't it? A tan inverse y by x. So differentiation of tan inverse is, I remember as far as I'm concerned, it is 1 by 1 plus x square, isn't it? 1 by 1 plus x square, is it? I'm not sure. 1 by 1 plus x square. Okay, so we're going to do it with respect to x, right? So we do minus 1 by x square also. 1 by 1 plus x square into okay, so we've got y square by x square. So okay, so let's do it clearly. We're not going to be confused. So let us assume that let us see that phi is tan inverse of y by x. dou phi by dou x is what we want. We have 1 by 1 plus y by x whole square into because this is y square by x square, what is the differentiation of this? It's gonna be y square into 1 by x square. Differentiation is gonna be minus 2. Okay, so this is basically x power minus 2 is nothing but minus 2 into x power minus 3, isn't it? So minus 2 into x power minus 3. So we have x square by x square plus y square into y square. This is basically minus 2 by x cube. So on a whole we have minus 2y square by x into x square plus y square. Okay, so we have something like this, and then we substitute it here, minus 2y square by x into x square plus y square. Okay, so this is what we get. Now that's how you get dou f by dou x. Okay, then you take this thing and substitute it in this gradient function dou f by dou x, and similarly you calculate dou f by dou y. But actually I'm not satisfied with this result because it is very concise, dou f by dou rho. So I was thinking, right, how can I solve this in that way? Okay, so guys, we are doing a small interchange of the problem here, because we are actually solving for dou f by dou x, isn't it? And then we are putting these complex functions, but we are always going to have an I cap, right? So that's a difference. Although this is also correct, this is not something which is wrong. So we will try to calculate dou. We're going to calculate the gradient, isn't it? So we're calculating the gradient of f in we're going to calculate rho comma phi comma z axis. Okay, so we have a rho cap, we have a phi cap, and we have z. So let me think on how we can actually generate this thing. So how do we do this? Basically we have a so let how can we do this? Okay, so let me show you. One idea that I got is we've got I cap, j cap, and k cap, isn't it? Now we know a way to convert I cap into a combination of rho and phi, and j cap also we can convert into rho and phi. Now how we do this? Basically it is nothing but rho cap is cos phi I cap plus sin phi j cap. Okay, and phi cap is nothing but minus sin phi j cap plus cos phi I cap, isn't it? Yes it is. So if I want to convert dou f by dou x I cap, okay, into rho cap and phi cap combination. Okay, so basically it is like this, guys. See, this is also something like problem solving. So you've got rho and phi, and then you've got a matrix cos sin minus sin cos, and then you've got I and j. This is I. So basically when you inverse this, you've got I and j is nothing but I'm taking an inverse, isn't it? So it's going to be a transpose because this is a Hermitian. So we've got c minus s sc, and then we've got rho and phi. I'm not sure if the inverse is correct, so let me check if the identity is followed. So cos square plus sin square 1, sin cos minus sin cos 0, sin cos minus sin cos, cos square. Yeah, so this is the inverse. So I cap can be written as cos phi rho minus sin phi phi. So if we are substituting such representations, we're going to get dou f by dou x into I cap is nothing but C rho, C is nothing but cos phi, S phi, okay, plus dou f by dou y into sine rho plus cosine phi. I mean, these are vectors. There's okay. So now it's gonna be rho cap into dou f by dou x, okay, into cos phi plus dou f by dou y into sine phi, okay. This is now coming in a clear way, and then we've got phi cap into dou f by dou x into minus sine phi. This is into minus sine phi plus dou f by dou y into cos phi. Okay, so now when we are actually solving for these things, we actually gonna get these results. So dou f by dou rho is nothing but this thing. So how we gonna get that also, I'll show you. So dou f by dou rho is nothing but dou f by dou x into dou x by dou rho, okay, plus dou f by dou y into dou y by dou rho, okay. So now rho, okay, so x is nothing but rho cos phi, y is nothing but rho sine phi, okay. So now this is nothing but dou f by dou x into dou x by dou rho is nothing but dou x by dou rho cos phi, isn't it? And then similarly we're going to get dou y by dou rho is nothing but sine phi, isn't it? So this is nothing but dou f by dou rho. Simple, na? Normal differentiation. So you can observe that this particular value is also over here, this one. So we can write this as rho cap into dou f by dou rho. Alright, now we are having dou f by dou, so here let us calculate what is dou f by dou phi actually now. So this is nothing but dou f by dou x, okay, into dou x by dou phi. Similarly for y also, this one, dou f by dou y into dou y by dou phi, which is nothing but dou f by dou x into dou x by dou phi is nothing but minus cos ka derivative is minus sine phi, is nothing but minus rho into sine phi, isn't it, plus dou f by dou y into rho cos phi, isn't it? Yes. So this is what we have here, but with a rho scaling. So this value is going to be replaced by 1 by rho into dou rho by dou f by dou phi. So finally what we are going to have is the gradient of f is dou f by dou rho into rho cap, right, plus dou f by dou phi into 1 by rho of phi cap plus dou f by dou z of z cap. So this is how we can actually calculate complex values with the coordinate transformations involved. So all that we need to remember is some simple transformations from one to another, such as this parameters and also the matrix method I just showed you. So this is all that there is to understand coordinate transformations and to solve various problems that are involved with coordinate transformations. So most important thing here is to understand what are the coordinate systems or what are the coordinates that you are dealing with, the definitions of the coordinate systems, and the standard properties, as in which vectors cross product leads to which. That is one important thing, and also a standard coordinate transformation to convert into your own comfortable coordinate systems back and forth. So this is all that is required to understand coordinate transformations, and I hope that in the future, if you're given a complex coordinate transformations, right, in higher dimensions or with the other coordinate systems, right, you can actually solve this in an easy way in this manner. So that's it for today. Let's talk about another problem in the next video. Signing off for now.